So let me try and walk you through the solutions to our free response number 82. It helps to read this thing through 2 or 3 times, but really we just want to start by simply reading the description of the situation. And by that I mean just the stuff above this red line. What is the given information that we're looking at here, and what do we want to do with it? Okay, so, oops, that didn't work well. I'm sorry, I'm just doing nothing here. That was dead space. We have a table here, and the concert tickets went on sale at noon, so noon is t equals 0, and were sold out within 9 hours. The number of people waiting in line to purchase tickets at time t is modeled by the twice differentiable function L for the closed interval 0 to 9. Values of L at t at various times are shown in the table. So let me break down for you what this is really telling us. First of all, do not freak out about this idea that the function is twice differentiable. All that means is that the first derivative and the second derivative exist, meaning that we can have a discussion about those two derivatives. Those derivatives are not in any way pictured right now in this table, but we're saying that whatever this function L of t is, that you can do derivatives like we're used to doing. So it's supposed to help you to give you that information. It's not supposed to freak you out. Secondly, our function L is only defined for 0 to 9. So anything outside of that interval between noon and 9 p.m., this function doesn't apply to, because we started selling at noon and we stopped 9 hours later. There is no other information. Okay, so these t values are associated with the L values, and you can think of these t values as x values and the L values as y values in a traditional abstract function. Okay, I'm going to read through quickly letters A through D, but then we're going to take it one step at a time. So in letter A, we're supposed to use the data in the table to estimate the rate at which the number of people waiting in line is changing. So I just noticed right off the top that word rate is going to be important. Oops, I just did something funky there. And we want to name it at a specific time, 5:30, which for us is t equals 5.5. We're going to show our computations that lead to the answer. Basically what we're doing there is we're finding an estimate for the derivative at point t equals 5.5. In letter B, it says use a trapezoid sum with 3 subintervals to estimate the average number of people waiting in line. In other words, we're trying to estimate the average value of the function. Okay? And we know that to do the average value of function in calculus, we do the area divided by the length of the interval. When we have a function, we do the definite interval divided by b minus a. We don't definite integral. We don't have a definite integral here because we can't do the definite integral. We don't have the expression of the function, but we can estimate that area using this trapezoidal sum. In letter C, on the closed interval, what is the fewest number of times at which L prime of t must equal 0? And we'll give a reason for our answer. And finally, in letter D, the rate at which tickets were sold for 0 to 9 is modeled by this new function, r of t. So they're introducing an expression for r of t right there. I got to keep that in mind. And that's tickets per hour based on the model. How many tickets? We're trying to figure out how many tickets are sold by 3 p.m. Okay, that's a lot to think about right now. We're going to take it step by step, A, B, C, and D, one slide at a time, and see if we can get these solutions. In letter A, we are asked to use the data in the table to estimate the rate at which the number of people waiting in line is changing at 5:30. T equals 5.5. So basically, we're supposed to estimate L prime of 5.5. Now, we don't have a function L, so we can't do the derivative on the expression. All we have is this data. But remember, the derivative is simply the slope at time t equals 5.5. So if I go along my data here and I see where 5.5 falls, it falls right here between 4 and 7. If I compute the slope from 4 to 7, I ought to be able to estimate the rate of change at that time. So what we're going to do is we're going to do L of 7 minus L of 4 divided by 7 minus 4. When we do that calculation, we get 150 minus 126 over 3. 150 minus 126 is 24. And that's 8. So basically, we estimate the rate at which the people in line are changing is approximately 8 people per hour. Oops, I spelled hour wrong. I think you can see that there. Again, this is an estimate because I can't actually compute the derivative at that point. The best I can do is use the data that they gave me and estimate the slope between the two data points that I have. I have two data points that are near 5.5. I compute the slope there, and that's the best I can do. I just did the slope between those two values there. And that's it for letter A. Let's check out letter B. So in letter B, we are asked to estimate the average number of people waiting in line. They're basically saying, hey, what's the average value of the function? And we know that the average value of function is the area divided by the length of the interval. So that's where this trapezoidal sum comes in. We are going to use a trapezoid with 3 subintervals, in other words, 3 trapezoids. We will add up those areas, and then we will divide by the interval. For us, the interval is the first 4 hours, so that's 4 minus 0. Okay. So the trapezoid sum is going to look something like this. We're going to add up the y values from 0 to 1. So that's going to be 120 plus 156 over 2. Sorry, I'm trying to do two things at once here. So I'm going to do 120 plus 156 over 2 times the width of that interval, which is 1. That's my first subinterval. Then I'm going to do from 1 to 3. That would be 176 minus 1 or plus 156 over 2. And then the width of that interval is 2, because from 1 to 3 is 2. Plus, I got to do 3 to 4. My third subinterval goes from 3 to 4, and that's going to be 126 plus 176 over 2 times 1 again. And in case you've forgotten, the way we approximate with trapezoids is we average the two y values on either end, the right and left. We average them and then multiply by the width of that interval. So looking at this chart here, the first interval goes from 0 to 1. The second interval goes from 1 to 2, and the third interval goes from 2 to 3. Or excuse me, 3 to 4. 0 to 1, 1 to 3, and 3 to 4. So this one has width 1, this one has width 2, and this one has width 1. That's where these values come in. And then the average of the two sides of the trapezoid are just the y values. Now, we have to take that whole thing, whatever that equals, and we have to divide by 4. All right? And when I do this entire calculation, it works out to be about 155.25 people. You add up that area there by multiplying out this top expression. You divide the whole thing by 4 because that's the interval, right? We're dividing by 4 minus 0. And I just cranked this out on the calculator, but it's approximately 155.25 people. That's an estimate for the number of people waiting in line in the first 4 hours. And truthfully, since you can't have a quarter of a person, I would say the estimate is 155 people. And I would leave it at that. But 155.25 is what you get when you crank out this math on the calculator. Let's take a look at letter C. So the wording on letter C is interesting. And it's going to challenge you to think conceptually about the derivative of this function L, since we don't have very much information about it. But essentially what we're looking for is the fewest number of times where this thing's going to equal 0. In other words, it's going to equal 0 at least this many times, whatever this number is that we figure out. It might equal 0 more than that, but it's going to be at least that. And so what we're going to do essentially is we're going to show where this derivative is positive and where it's negative, and then using the intermediate value theorem, we will be able to say that if it's positive somewhere and negative somewhere, it's got to cross 0 in that interval. And we're going to be able to do that because we were told that this function was twice differentiable, meaning that implies to us that the derivative is continuous. Because if the derivative is differentiable, in other words, if the second derivative exists, it means the function is continuous. Okay, so bear with me here while I do a little math. As I look at these values for L of t, I notice that from 1 to 3, I have a positive slope because I went from 156 to 176. And then it changes to a negative slope on the next interval because I go from 176 to 126. And then again, it's positive on 126 to 150, and then negative again on 150 to 80. So I essentially have it changing signs somewhere in each of those intervals at least 3 times. I've got a change here, a change here, and a change here. I don't know exactly where they are, but I know that it has to exist by the mean value theorem. So what we're going to do is just write a little math and a little bit of explanation to explain our ideas, and then we'll have a solution here. So let's just compute some slopes. Since L prime of t is positive on 1, 3. Actually, let me make that a open interval 1, 3. Where's my eraser? Sorry about this. 1, 3. And the calculation that I have for that is that 176 minus 156 over 2 is positive. Since L of t is positive on 1, 3 and negative, oops, let's do this in blue again, dude, and negative on 3, 4, gosh darn it, I just screwed all that up. I hit some weird button and resized the picture there. Sorry about that. I did it again. I'm touching it twice, 2 places at once. I need to put this thing on. All right, you don't even know what I'm doing, but anyway. And we're negative on 3, 4, and my justification for that is the calculation 126 minus 176 over 1. That's negative. Okay. Since I'm positive on 1, 3 and negative on 3, 4, there must exist, the mean value theorem says that we must be equal to 0 somewhere in between those. The intermediate value theorem, excuse me. What am I doing? It's actually a combination of the mean value theorem and the intermediate value theorem, but I'm going to use IVT for short, but you should write that out if you're taking the test. The IVT tells us that L prime equals 0 somewhere in 1, 4. Somewhere between 1 and 4, we're going to have a 0. And we play the same game similarly. We must have a change between 3 and 7. right? Because we are negative on 3, 4, and we're positive on 4, 7. So I'm going to just write here, because I'm running out of space, that L prime of t equals 0 in between 3 and 7, because that changed sign in there somewhere. And also between 4 and 8. Not the most articulate answer, but I think you'll agree that we went from, if we did a sign diagram on this thing, we went from positive to negative to positive to negative in terms of our slopes. And so somewhere in those subintervals, we're going to have places where it equals 0. And therefore, the bottom line is the answer, the answer is at least 3. That's the minimum number. The minimum number of times, the fewest number of times that L of t will equal 0. It has to equal 0 at least 3 times. It could be more. Holy smokes, that was awful. All right, maybe I can do a better job on letter D. As I mentioned on the first slide, in letter D, we're given a formula for R of t, which is a function that tells us the rate at which the tickets are sold per hour. Okay. In other words, R of t is a derivative. And we're trying to figure out how many actual tickets were sold by 3 p.m. Since we started at 0, we're actually trying to figure out how many tickets were sold between 0 and 3. This is your classic accumulation problem. If we want to compute the number of tickets sold from 0 to 3, we simply integrate from noon, which is 0, to 3 p.m., which is 3, the R of t function, which is 550 t e to the negative t over 2 dt. If we do this definite integral, we will find out approximately how many tickets were sold. Actually, we'll find out exactly how many tickets were sold based on this formula. And to save time, I'm going to run this through my FNInt on the calculator, and when I crank it out, I end up with 972.784 for the value. Now, that's the value of the definite integral, but you can't sell a part of a ticket. So you're either going to say 972 or 973. I'm going to round it up, and I'm going to say that we sold 973 tickets. Oops. Of course, I have to write the number correctly to do that. I keep pressing the wrong buttons here, which you can't see, but you can see me stalling. Come on, man. 973 tickets. Okay, now just to be clear, since this is a rate, and we want to actually figure out the number of tickets, which is an accumulation of those rates, we simply integrate over that time period. We do the definite integral of the rate. Come on, baby. My buttons just aren't working here. We do the definite integral of that rate function, and that's how we figure out how many tickets were sold in that time. 973 tickets over the first 3 hours. Okay, that video was way longer than it should have been, but hopefully this will answer any other questions you have until I see you again. Take care.